Hi, my name is Garrett Edmondson, and welcome to another in my series of videos about data warehouse and ETL. This series of videos is focusing in on ETL, the different aspects of ETL that are important when constructing an overall data warehouse solution. As before, if you've not seen the previous videos, I highly recommend that you at least start at the beginning of this series of videos, as they cover important concepts that I might briefly mention and that have much more detail behind them. So, to begin with, today's video is going to be about table partitioning. Table partitioning is one of the best ways to get good performance out of your ETL process. DML, or data manipulation language, consists of inserts, updates, and deletes. One of the chief complaints I hear about the dimensional modeling is the size of fact tables. Many people are intimidated by fact tables that are many multiples of billions of rows, and that being able to perform updates, inserts, and deletes on those tables can take too long. So therefore they try and invent new ways to make those tables very small. However, table partitioning can overcome many of these perceived difficulties with managing fact-type data. It may also improve, depending on your situation, query performance as well. Depending on how you're able to partition your fact table, you can actually get better query performance. And this is not in all cases, and particularly with the introduction of column store indexing, query performance increases through table partitioning might be negligible, because column store indexes are just so much faster to begin with. So, to begin with, I'm going to cover a little bit of theory around table partitioning. And how to use table partitions to perform switching, which is the primary function, or the whole reason why you would want to partition a table. This is a very complex subject, and I'm only going to cover the basics as it relates primarily to dimensional modeling and ETL. Other resources are available on the net that I will make links to in my video that will provide greater detailed information about this subject. So, to begin with, at a high level, table partitioning, you should consider table partitioning for your fact tables. Virtually every fact table should have table partitioning on it, simply because these tables have a tendency to grow very large very quickly. So let's say I have a fact table which has 2014 to 2011 data in it. And so it's one fact table. All these rows are contained in one table. Now, as the name implies, you can partition that table by a column, a fact column. And in most instances, this fact column is a date column of some type, a transaction date. And so by doing that, your fact column is exposed to your queries and to the end users and any applications querying this data. It still looks like one fact table, but really underneath the covers, this fact table has been horizontally partitioned or divided up into discrete units here. So all of 2014's data is here, 2013, 2012, and 2011. And so now these independent data partitions can be operated on without affecting the neighboring partitions. And so this can make your DML, or data manipulation language, operations much more efficient. And in SQL Server 2012 and higher, you have access to 15,000 partitions. And so you can really partition your fact table up into many partitions in order to really make small discrete DML operations on these partitions. So that's how it works. These partitions are connected together with metadata, essentially pointers that connect these all together to one fact table. And partitioning is smart enough that when it gets a query, let's say you're querying your where predicate only requests 2013 data, then that query will only be pushed down into 2013 as required by your predicate logic. So now you understand a little bit about what partitioning is and how the table gets divided up. then partition switching is the act of switching these partitions in and out of a partitioned table. So in this fact table, again, I have it partitioned by year in this example, keeping things very simple. And I have a 2013 data that I want to either update, insert, or delete. And so what I can do is I can create a new version of that data through DML operations, and I can actually switch the new version of the data for the old version of the data. And because this is only, these partitions are only tied together in metadata pointers, essentially all that needs to occur is to have the metadata pointer, instead of pointing to the 2013, the old version of the data, it is now pointed to 2013, the new version of the data. And so now these queries coming into the fact table will have this new version of the 2013 data supporting it and the result sets. And so the purpose of this slide is simply to emphasize that this is a metadata only operation when done correctly. Now, not in all circumstances, and again, you have to read the books online and read the circumstances as to when this is a metadata only operation and when it is not. But ideally, it is only a metadata operation that changes these pointers that point to these individual partitions. So that's really the speed and the in terms of ETL processing of fact data. So this will work a few different ways. For instance, for a bulk insert of fact data, you can use table partitioning to perform this operation in parallel with many bulk inserts occurring at the same time. And what this might look like is the following. I create my new partitions, my stage fact, if you will, 2014, 2013, 2012, and 2011. The final destinations are going to be in my fact table, but I can go ahead and load these guys up in parallel with parallel bulk inserts all at the same time, and then perform my switch. Again, because it's only a metadata operation, now my sales fact table is populated with my data on a yearly basis here. So this is demonstrating how partition switching would be used for a bulk insert scenario. You can then drop these partitions if you so desire. These are empty partitions because they've been switched out, and the new data is now on the left-hand side, although there was no data movement occurring. You can then drop these stage partitions if you so desire. Updates. So this is very important if you want to make large-scale updates to your fact table, which occasionally is necessary, but should be minimized to the lowest extent possible. You should ideally never have to update your fact data. Ideally it's insert only, but occasionally large updates do have to be performed. And so in this case, partitioning can really improve performance of these types of operations. So here again, I have my 2014 through 2011 fact table that's been partitioned by a year. I have a new incoming row set here that I build. One of the things that I can mention right now is that your schema of the partition that you want to switch has to be identical to the target. This is very important. It has to have identical column names, data types, and even aligned indexes. So what that means is indexes with the same definition. Obviously they can't have the same name, but they have to have the same definitions in terms of the columns that are included in those indexes, as opposed to the destination fact table. So here I have my new version of my fact data, and I might have to do some sort of delta detection on that. So I do a bulk insert, and then I can switch out my old fact data. So then I'm only comparing, in this case, I think it'll be 2013 to 2013, the old one versus the new, or it's 2014, I'm sorry. And by doing the delta checks on a subset of the data, I can do a filtered select into the new version of that data. And once that is populated, then I can just switch it back in and remove these other partitions. So again, the whole purpose of this is that I have a new incoming version of these rows, massive updates that I need to perform. I put those into one partition. I switch out my old version of that data. I do a filter, basically a select join kind of filter, where I get the new version of my fact data, which is then switched back into my fact table. And so this can greatly improve update operations on your fact data. Next is large deletes. Now with large deletes, partitioning is very useful, and this is also an important factor when thinking about data warehouse and management of your data warehouse data. Your fact table should, by necessity, be pruned every so often at a regular interval. Let's say at the beginning of the new month, a month's worth of data is actually taken off the backside of the table, meaning that your table, let's say, for your requirements requires 5 years worth of data. And so every month at the beginning of the month, the month that is 5 years old, that month's worth of data is removed, and then new data is obviously inserted throughout the month. It's very important that you have a pruning process, or a process of archiving out old data in your fact table. This can even be archived off to a new file group, or a new set of disks, or a slower set of disks, less expensive set of disks, something like that. There's many different ways of handling this. So, however, typically, in order to do this, you need to delete data, and deletes are very costly with large fact tables, and so partitioning really shines here. So for large deletes, what happens is I'm going to produce a partition based off my 2014 partition, and I'm going to filter out all those rows that I don't need. Let's say, in my example, a month's worth of rows. And so what's going to happen there is I'm going to produce a partition using bulk insert. Remember, in my where, I'm going to filter out the stuff I don't need and bulk insert it into a partition, in this case 2014. And then I'm going to switch out the old partition. So here goes the old partition, switching that out, and I'm simply going to switch in the new filtered partition of 2014. And this way I can perform very large scale deletes. And let's say I have to, for whatever reason, delete a particular dimension member from all these years. Well, I can run one very big large delete statement, which would take a long time and really chew up your transaction log, or I can start doing it using this method, using a filtered bulk insert and then switching it back in, and do that in this case on a yearly basis, and go through my years like that as a much more performant solution. So that's enough for the basics of how you perform DML operations using partitioning. Now I'm going to show you an example. Again, this is going to be a very simplistic example, and there's many more aspects to partitioning to consider, but this will just give you an idea of how this all runs and operates. So to begin with, in Management Studio here, I have a series of commands, and so just so you're familiar, it should be very familiar to you, but if it is not, for a database, you have underneath storage 2 folders or directories here that are for table partitioning and setting up table partitioning. One is functions and the other is schemes. And so when I create these will be created here. So first off are partition functions. And a partition function, you give it a name, and then you give it a range of values. And so these values represent the endpoints, or how you're going to partition your tables that use this function. And so these are the endpoints for the values, and you can either partition with a range left or a range right. Depending on your requirements, you need to be able to choose the right one. There's lots of good documentation with this. For this purpose, I'm just going to define 3 endpoints here. And you can tell probably from, even though these are integer values, that I'm partitioning by day. Because SQL Server allows 15,000 partitions, that's roughly equivalent to 41 years worth of data. And so that you can get very granular with your partitioning if you choose to. So this is my partition function for my table partition demo fact table. And then I'm actually going to create another partition for the switch table that I will use to switch data in and out of this fact table. Now you don't have to do this. You can have both the fact table partitions and your switch partition use the same partition function. However, I'm just showing one of the many ways to do this. Again, I'm going to define the same endpoints, so there's going to be 3 partitions, and they'll have identical endpoints to my my fact table, my target fact table. So once I create those, then underneath, if I refresh, then underneath my partition functions, I will see that they are created there. Now I'm going to create the schemes. And so the schemes, now that I have the definition of the functions, the schemes are actually going to define where I keep this data. Partition has the ability for you to keep different partitions on different groups of disks, different file groups and things like this. And this can be very useful when you want your most recent data, that data is most heavily queried, to be on the fastest set of disks, whereas most expensive set of most expensive set of disks, let's say they're SSDs or something like that. And then you can have a separate definition, part of your partition scheme to partition the other partitions on other sets of slower disks, cheaper disks. So, however, for my purposes, I'm going to have just all of these partitions created on the primary file group. Go ahead and do that. That's why it didn't show up. Okay, so if I go back to storage here, here are my partition functions that define my endpoints. I have 2 of them. I can use the same partition function for many tables, but in this case I'm just dividing them up. And then here are my partition schemes that define where these partitions will live in terms of file groups and things like that. But for the purposes of this simplicity demonstration, this will all be on the primary file group. So then I can use a series of views to view these partition functions and schemes and information related to them. So here, here they are. And you can tell me the range, the create time, and then the values, the boundary values. And this would be the partition number, and then the value, the boundary on those. So I created 2 partitions each. Sorry, 2 partition functions with 3 partitions each, and so that's a total of 6. So this can become important and good, valuable information. So now what I'm going to do is I'm going to create my fact table. This is going to be my target fact table. It's just going to be a partition table. And the important thing here is, instead of designating a file group, what I do is I designate my partition scheme. And if I have multiple file groups and a more complex strategy here, then my partition scheme will define where each partition will reside on which set of disks. I also have to feed it the column that this is going to be partitioned by. In this case, it's going to be order date, which in most fact tables is going to be some sort of date column that you're going to use. So, I'm going to create that table. And I'm going to create my switch partition right now. You don't have to do this ahead of time like I am doing right now. You can do it dynamically during your ETL process, creating your switch partition, your switch table, and then dropping it. However, because I created a separate partition scheme, underscore switch, then I will use that scheme. And again, I'm partitioning by that same column, that order date column. Other than that, it has identical column values, and it must have identical column names and data types and indexes to be able to switch in and out. However, in my example, I'm not including indexes as just to keep things simple. So what I'm going to do now is insert data into my fact table. This will represent the current state of my fact table with historical data already in it. So I inserted 60,000 rows. Now I'm going to simulate an ETL process coming. And this ETL process is going to load more current data into the switch table. So this is data for 801. 730 is going to be the max data of my historic fact table, and I'm loading in the next day's worth of data. And so I'll do that right now. 60,000 rows are loaded into my switch. So now, if I look at my fact table, my max order date value is 731. All right, 731, that's the max date. And now through my ETL process, I've loaded up my switch table. And it represents the next day's values, 801. So this is a typical daily load situation for your fact table. And an important thing to note here is, also that this is probably some things that you want to build into your ETL process, is the use of this $ partition. This is very important because this will tell you for any given value what, in a partition function, it'll return what the partition number is. So that's number 2. So for the partition function of the fact table, the next day's worth of data is going to be in partition number 2. When we do this switch, the switch command uses partition numbers, and so you have to look up the partition number for your data prior to actually performing the switch. And if I actually try to select data out of my fact table for that partition, I get nothing back. So this way I know that the destination fact table, its partition that I want to switch into, is empty. This is very important. Your target partition needs to be empty. If there is data there and you try switching it in, you will produce an error. So now is the switch. So the switch is an alter table command, and first you always put your source table that you're switching from. So that's my table partition fact demo underscore switch. That has the 801 values, the newest values. And I'm going to switch that partition, partition number 2, into, and remember it's partition number 2. There's 3 partitions on this using the partition scheme and function here. And I'm switching that to my fact table. Partition number 2 as well, because these have identical partition boundary points. So, and that's the instantaneous nature of the switch. There's no inserts that I have to perform. It's simply a metadata operation. And if I go back, now I can look at my max date, and it was 731, and now it is 801. And if I look at my order date from my switch table, there's nothing there. Why is there nothing there? Because the original partition on the fact table was empty, and I just switched that for my switch table partition, and that which had data in it. And so now my switch table is empty, and my fact table is loaded up with that new 801 data. And if I want to switch it back, do the opposite, it's the same process. So now I'm switching out of my fact table, and I'm going to switch the second partition to the switch table. And that's going to be the second partition as well. And if I execute that, then things are back to the way they were. The max value on my fact table is 731, and my fact switch partition has only 801 data in it. So now I can operate on just a subset of the data on my switch partition here and switch it back in as needed, just like I demonstrated in the previous slides. Okay, so now I'm going to go over some few basic guidelines to keep in mind. First and foremost, look up the data loading performance guide from the SQL CAT team. This is a wonderful document on how to perform very fast load operations. Basically, and I'm not going to go through that whole document in detail, basically what you want is to ensure, given your requirements and your environment, is that you have a minimally logged operation. And this will greatly enhance the performance of your inserts. So, and again, speaking really high level here, you want to make sure that you remove any indexes, so you're inserting into empty tables for your switch tables, for your stage tables. You can actually use an order by hint, particularly if you have a cluster index on your fact table. Ultimately, you can have those things pre-sorted so that they reduces the processing of the data. You can use tab lock, and you can insert in parallel, and it scales linearly to about 16 streams if you're not I/O bound. And this is particularly important. I want to emphasize that this relates back to one of my previous videos, that if you have gone through your SQL I/O testing and you know exactly what your throughput capability is in terms of your writes, then that will be directly correlated to how fast these inserts can occur. If you can insert 1 GB per second worth of data, then and you know that's your capabilities of your hardware, and that's what you're getting out of your SQL Server bulk inserts, then you know that you've maxed out your hardware, that you're actually getting all the I/O that you're capable of. And you might reach that max I/O at 8 or 4 simultaneous streams, but you know once you've hit your hardware max that you won't be able to get any more out of it, that you've tuned it to the best way possible using the guidance from the data loading performance guide. Remember, in SQL 2012, there are 15,000 partitions. There's actually ways to do things a little bit more than that. You can use things like partition to views, and in combination with partition tables to actually get many more than that. I'll provide links for that. Remember that when you're switching, that if you're in the same file group, it is a metadata operation. However, if you're switching partitions between file groups, it is not a metadata operation. You actually create a duplicate set of data in the source file group, and then that is actually transferred to the target file group. And so you need to be very careful and understand very thoroughly what you're doing if that's something you have to do. But sometimes that's unavoidable. Another key thing is the target partition must be empty. Otherwise, you will receive an error. And it's very explicit. It tells you that the partition is not empty and it needs to be empty. So you can load the stage table with bulk inserts using tab lock. Again, there's certain conditions when this is true and this is the best way to do it. Refer back to the performance guide for help there. So now here is kind of putting things together. Now you hopefully have an understanding for the basis of what I'm going to explain here. Here's just a partition switching pattern. Here I have on the left-hand side multiple source databases. Let's say they're SQL Server or some other database engine. And so what I can use is I can use integration services to pull simultaneously in parallel, if I can, all this data. I can perform the surrogate key lookups in the pipeline, and then just stage the data directly to my fact stage table here that's partitioned, right? And I've dropped all the keys previous, so I'm just inserting into an empty table. And you can roughly, this is a rough thing, and you need to test it, but you can perform the number of concurrent bulk loads that you can perform is roughly equal to the core. So you can spin up a load per core and get parallelization that way. That's also provided that your pipeline has enough throughput to be able to do this. Remember that your connection from your data warehouse server to your sources is usually the slowest part of any overall data warehouse solution. So you need to be very careful in making sure you understand the consequences of that. But provided that you have that kind of throughput, yeah, here we go. So once the data is loaded, then you can create your indexes. Make sure you sort the indexes using tempDB. This is really important if you want to get reduced fragmentation of your indexes. And even though it takes a little bit more time, using max degrees of parallelism set to 1 when you create your indexes provides you with the most pristine indexes, so the lowest amount of fragmentation. And so you're ensuring that once that metadata operation, that switch occurs on your fact table, that you have the most pristine set of data to get the best sequential reads out of this, and thereby the best performance, largest block sizes. So that's the first pattern with integration services. Now, in most situations, you also have things that require source flat files to be staged up, and so this is almost identical to the previous. Bulk inserts. Remember, this is the fastest way to bridge the gap between your sources and your data warehouse, because you can compress these files and transfer them over the wire in a compressed format, and so this is the fastest way to do things. And again, the basic suggestion here is your number of concurrent bulk inserts can be equal to roughly to the number of cores. So you can do bulk inserts there, and the same guidance applies for once you've inserted into the empty table, you can then create your indexes and continue on with the switch. And so those are two basic patterns. Another pattern, and this goes back to a previous video when I showed how you need to create file groups that are the number of file groups to be aligned to the number of cores in your system. If you do that, then you're using the NUMA kind of type methodology or approach that for memory and processor, and actually pushing that all the way back down into your database files in your file groups. And that was in my parallelism video. And if you didn't understand all that, go back and watch that video, refresh your memory. So here I've staged up, I have a kind of a target database staged up like this, and here are my file groups and my partitions that I have then created on my file groups. And so I have several source files coming in, and how this would work. There's my destination table represented by my fact tables. I do concurrent bulk inserts into my first heap stage table, and this is in a separate file group. And then I do, again, 8 concurrent inserts into individual stage tables here that are partitioned. In this case, these will have the clustered index as part of the keys. And the third and last thing here is then I can create, with the clustered index, compression, and I can insert into the final stage tables here by file group. And so remember, however, with this kind of thing, with the transform in the third step, that you need to be careful in terms of the data movement of your file groups, making sure they have enough data here, because every time you cross a file group, it's not just a metadata operation. And the last step, of course, is just to switch in the file groups. And so all this is happening in parallel on multiple file groups at the same time. So it's a very fast type of way of loading your data. And because it's NUMA aligned or pseudo-NUMA aligned, you get the processor affinity to each one of these file groups. And so this is following the Dell Quick Start Fast Track recommendations here. So that's all I had for this video. If you didn't understand all these concepts in this more advanced type of scenario, that is okay. It is something that's fairly advanced, but what I wanted to emphasize is the basics in terms of the fact and the switching of the data and how that can affect DML operations. Thank you for your time. Goodbye.